topic is simple harmonic motion. We're going to be dealing mostly with springs, pendulums today. So simple harmonic motion is a type of what we call periodic motion. We might also call it vibrational motion or oscillatory motion. You know, oscillate means to go back and forth. During periodic motion, there's this one spot in the path of the object where there's no net force acting on it. We call that the equilibrium position. So if we're talking about springs, that's when the spring is not stretched or compressed at all. It's at its natural length. If we're talking about a pendulum, we're essentially talking about when the pendulum is straight up and down, when it's vertical. But when that object is pulled away from that equilibrium position, now there's a non-zero net force acting on it. And that net force always pulls the object back toward equilibrium. We call that force the restoring force. So realize when we're talking about the force in springs or the force in a pendulum, that force that's always pushing or pulling the object back toward equilibrium, it's the restoring force. If the restoring force is directly proportional to the displacement of the object, the motion we call simple harmonic motion, and you'll oftentimes see it called SHM, simple harmonic motion. It's only simple harmonic motion if the force, the restoring force, is proportional to the size of the displacement. That's important. Also during SHM, the acceleration of the object is proportional to the displacement. A couple of terms to be familiar with when we're talking about simple harmonic motion. Period, we capitalize it with a big T. That's the time for one complete cycle. It's not up here on the screen right now, but frequency is the number of cycles per second. And amplitude is another word for the maximum displacement of the object away from equilibrium. So those are important terms that we'll be dealing with throughout today. And let's see. So an important idea related to simple harmonic motion is Hooke's law. So Hooke's law says that the restoring force due to a spring is proportional to the length the spring is stretched or compressed. We could add the word compressed there. The force always acts in the opposite direction of the displacement. The formula for Hooke's law, as you can see here on the screen, this is essentially Hooke's law in a formula. F equals negative kx, where F is the restoring force. It's the force that always pushes or pulls the object back toward equilibrium. Let's talk about x next. X is the displacement. So how far has the object been moved away from the equilibrium position? And then finally, K is the spring constant. Sometimes you'll hear it called the force constant, but usually it's the spring constant. And it essentially relates to how strong the spring is. It measures the strength of the spring in terms of newtons per meter. Notice the negative sign in Hooke's law. That negative sign tells us that the force is always in the opposite direction of the displacement of the object. That's why that negative is always there. Force is always in the opposite direction of the displacement. We'll see if I can clean up my screen a bit here. So a couple other things to be familiar with once I get the screen cleaned up. The formulas that you see up here on the screen are on your AP formula sheet. So you don't have to memorize them, but you do need to be very familiar with them. Just a second to get this menu straightened up here. All right, so we're going to deal with really three things when we're talking about simple harmonic motion. Masses on springs. It could be a mass on a vertical spring, like hanging up and down. It could be a mass attached to a horizontal spring that's moving back and forth horizontally. That works if we're ignoring friction, if there is no friction. And we'll also talk about pendulums. Let's talk first about springs. When we're dealing with springs, one important thing we need to talk about with simple harmonic motion is the elastic potential energy stored in the spring. And we've got a formula you can see here on the screen. 1/2 kx squared is equal to the elastic potential energy. Again, K is the spring constant measured in newtons per meter, and X is the displacement away from equilibrium. And again, you want to make sure that's measured in meters. If it's not given to you in meters, convert it to meters before you do your calculations. We'll deal a lot with that formula here in a minute. We also can calculate the period of a mass attached to a spring. And notice the formula here for the period of the mass attached to the spring. So it's 2 pi times the square root of the mass of the object divided by the spring constant. So 2 pi root m over k. Both of those formulas are going to be important here in just a couple of minutes. All right, so let's start off by looking at an example of simple harmonic motion, and let's do that from a picture. Once again, let me clean up the screen a bit before we get started. Let's start with the object at the equilibrium position. So that would be the middle picture here. So for right now, our object is at equilibrium. I'm struggling with my screen. Bear with me for just a minute. All right, so you see the blue line. That's the equilibrium position. So position number 2, the object is at equilibrium. So let's say that in equilibrium again means when the spring is at its normal, natural, unstretched, uncompressed length. Notice that when that's the case, the restoring force is 0 because the object is already at equilibrium. The acceleration is 0 because there's no net force acting on the object. We'll talk about the velocity in a minute. It turns out it's going to be a maximum at that location, but we'll come back to that one in a second. So let's say now that we stretch the object back, and let's go up to position number 1. So we grab the object and we pull it back to a displacement of A. Remember, A here stands for amplitude. That's the greatest displacement. So we pull it back to the greatest displacement area, and then we let it go. As soon as we let it go, since it's at maximum displacement, due to our F equals negative kx, Hooke's law, when the displacement is at a maximum, the restoring force is at a maximum. So back here, we've got our really big restoring force. And that's going to pull the box back toward equilibrium. But as it goes back toward equilibrium, the displacement gets smaller, which means the size of that restoring force also gets smaller. And we'll show that here just in the size of my F's. So back at the back, it's very big. But as you get closer to equilibrium, that restoring force gets smaller. And even smaller. And even smaller. Because remember, it's getting smaller because the size of the displacement is getting smaller. And then eventually we get to equilibrium and that restoring force is 0. Now let's also think about something else here. Because the force is getting smaller and smaller, that also means the acceleration is getting smaller. So back here at the back, acceleration is at a maximum. And I'll use a little a for that. So back here, we've got the biggest acceleration possible. But as the box moves closer and closer to equilibrium, that a gets smaller and smaller. And it continues to get smaller until at the equilibrium position, once again, a is 0. So they're going to ask you about things like the size of the restoring force. They're going to ask you about the size of the acceleration. They're going to ask you about the velocity. So it turns out, again, maximum acceleration back here at the back. It accelerates until it gets to equilibrium. It's not accelerating anymore. But at that point, the velocity is at a max. So here we have the biggest V possible. So now let's pretend that the box is now continuing to move to the left. So we pulled it back to the right, we let it go, and now it's moving back toward the left. So as it goes to the left, the spring is now compressing, which means the restoring force is now pushing back toward equilibrium. So the restoring force is now pushing back to the right. Starts off pretty small because the displacement away from equilibrium, pretty small. But as we move back further and further to the left, that restoring force gets bigger and bigger and bigger. And it's always pushing back toward equilibrium. And it's going to continue to get larger until it gets back to the maximum displacement at the back, which is going to be -A. And we can see that down in position 3. Did I hear a question coming in? So the maximum displacement, what we're seeing back here, -A. At that point, our restoring force is at a maximum, which means our acceleration is going to be at a maximum. And in this case, they're both acting this way. At that point, at that one little instant in time, at maximum displacement, the velocity is 0 because it stops for just an instant and then it reverses direction. And in this case, it'll head back toward the right. Now, something else they may ask you about is kinetic energy. So remember that kinetic energy, at least linear translational kinetic energy, is equal to 1/2 mv². So the kinetic energy is always going to be the smallest at maximum displacement, because remember, that thing stops when it gets to maximum displacement. When it starts heading back toward equilibrium, it starts to accelerate. When it gets to equilibrium, we have the maximum velocity. And because kinetic energy is proportional to velocity, the kinetic energy is also a maximum at the equilibrium position. During this whole thing of simple harmonic motion, the energy is being converted from elastic potential in the spring to kinetic. And then it goes back to being elastic potential over and over again, assuming there's no friction. So the elastic potential energy is going to be at a maximum at maximum displacement. So here's our symbol for elastic potential energy. When that box is way back here, it's at maximum. When the box is here in the middle, all the energy is kinetic. So in this point, the elastic potential energy is 0. All right, so let's keep that same idea, and let's look now at what a vertical spring situation might look like. Before we do, though, let me do a lot of cleaning up here on the screen. And I'm going to try to change computers here in a moment. I think my update is finished. I'm going to get to the next screen, let you guys look at it while I'm getting the other computer up and ready to go. All right, before we get there though, let's think about this particular graph here. So this is showing us a position versus time graph for simple harmonic motion. So at this point, and let's think of this as a horizontal spring for right now. At this point, let's think of that, that box being all the way over to the right. So we've stretched the spring as far as we can. Now we let it go. And when we do, it starts moving back toward the left. And you can see that our position's going down. It's going back toward the left. So when it gets to this point, to the 0 on the x-axis, that means it's back at equilibrium for that instant. Turns out that takes about 1/4 of the period, 1/4 of one cycle. So now the object continues past equilibrium because it has inertia, even though there's a net force acting back toward the right on it, slowing it down. Eventually, it's going to get to its maximum negative displacement, negative A down here. At that point, we're at 1/2 the period as far as time goes. The spring's going to compress, 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 maximum compression. At that point, the box stops and the spring pushes it back in the other direction. So it starts heading back toward the right. It's going to cross the equilibrium point again, right in here. At that time, we're at 3/4 of the period. It's going to continue back toward the right until eventually it gets back to where it started, maximum displacement on the right. So the time for it to go from maximum displacement on the right, for it to move to the left, back to equilibrium, and back to the right, that time is 1 period. And notice I've got a question here on the screen. I'd like for you guys now to go to the Pear Deck window for just a minute. And go ahead in Pear Deck. Make sure you're looking at Pear Deck and go ahead and do what it says here on the screen. Circle the points where the object has maximum kinetic energy. So go ahead and give that a try. Circle the points on the line where there's maximum kinetic energy for this block. Go ahead and take a minute and do that now. All right, again, guys, make sure you're in Pear Deck and you're circling the points on the graph where there's maximum kinetic energy. All right, I'm going to see what you guys are seeing. Just show your responses. So this person put some dark spots on the axis. Same thing here. All right, looks like you guys have got this. All of you put the same thing pretty much, and those answers are correct. During simple harmonic motion, the maximum velocity is going to be at the equilibrium position, which is at 0 here. So just like you guys saw, that would be right in here, right in here, and right in here. And that's true because velocity is a maximum there. The restoring force is equal to 0, the acceleration is equal to 0, but the velocity is at a maximum. And because K equals 1/2 mv squared, that means kinetic energy is also a maximum there. Kinetic energy is a maximum wherever velocity is at a maximum. All right, let's get to our next screen. All right, I'd like for you guys to take a minute and just read everything you see on this slide, and then we'll look at a picture and explain it, and hopefully by then I'll have my computer, the other computer, up and ready to go. So go ahead and read what you see on the screen, and I'll get logged in with this other device. All right, I'm going to go ahead and go to a picture here while I'm finishing up what I'm doing. So let's start off with this spring. So let's say that right now, the way it's pictured, the spring is at equilibrium. So when it's at position B, that's the equilibrium position. So let's say now that we pull that spring down to C. So C would be its maximum displacement. And we let it go. So you guys know that once we pull it down to C and let it go, there's going to be a restoring force that pulls it back up toward B. At point C, that's the maximum displacement. That means the restoring force is at a maximum because the displacement is at a maximum. That means the acceleration is at a maximum at C. Also, the elastic potential energy is at a maximum at C. We let it go. That restoring force pulls it back toward B. And as it gets closer and closer to B, the magnitude of the restoring force gets smaller and smaller. The magnitude of the acceleration gets smaller and smaller. The magnitude of the elastic potential energy gets smaller and smaller. But the magnitude of the velocity and the kinetic energy get bigger and bigger. So that when they get to B, those two are at they're at a maximum. All right, the thing's going to continue to move past B because it has inertia. And as it does, it's going to compress the spring. And now the restoring force is going to be pushing the ball back down. So as the ball continues to move closer and closer to A, the size of the restoring force gets bigger and bigger. The size of the acceleration gets bigger and bigger. The size of the elastic potential energy stored in that compressed spring gets bigger and bigger. And the velocity and the kinetic energy start to decrease until we get to A, where the ball will stop moving for an instant. So at A, maximum displacement, the velocity is 0, the kinetic energy is 0, but the elastic potential energy, the restoring force, and the acceleration are at maximums. And the graph you see here on the right is a really good illustration of that. Let me log in with this other device, and I think I'll be able to do a better job with it. Bear with it. And I'm going to work from the PowerPoint screen first or the Zoom window. So make sure you're looking at Zoom. So here's another picture of a vertical spring kind of scenario. So the dotted black line represents the equilibrium position. So you can see that in this first picture, we're at equilibrium. The displacement, X, is 0. Right now, the thing's not moving, and there's no net force acting on it. Now we grab the object, and we pull it down just a little bit. We'll go over to the second picture. And at that point, when we pull it down, our X is at a maximum. We now have a displacement at a maximum. Got somebody chatting with me, so let's see. Okay, so you got the join code QAEWBB. We'll get you into joinpd.com. So down here at our maximum displacement, our velocity is 0 because we haven't let it go yet. Our kinetic energy is 0 because our velocity is 0. But our restoring force is pushing that or pulling that object back toward equilibrium. And at maximum displacement, that restoring force is at a max, and it's pulling up. Also, because our spring is stretched to a maximum, our elastic potential energy, 1/2 kx squared, is at a max because this x is at its maximum value. All right, now we let the box go. And as we let it go, it starts to move back up toward equilibrium. And remember, the closer and closer it gets to equilibrium, the smaller and smaller the force, the smaller and smaller the acceleration. So picture 3, it's at equilibrium. At that point, its velocity is at a maximum, and it's still moving up. The net force acting on it is 0 because the displacement is 0. The kinetic energy is at a maximum because the velocity is at a maximum, and the elastic potential energy is at 0
because the spring at that instant in time isn't stretched, it isn't compressed. All right, so now we move on over to the fourth picture. Our box didn't stop when it got to equilibrium. It continued upward because it had inertia, had velocity, had momentum. Think of it that way. And as it goes up, remember that spring starts to get compressed. So now we have a restoring force that is pushing the block down. And the further and further we get away from that equilibrium position, the bigger and bigger that restoring force gets, and the bigger and bigger the acceleration gets. Let's say that we get up to the maximum displacement above here. So now let's say X is at a max. At that point, our velocity stops. That's the point that the block stops moving for just an instant. The restoring force is at a maximum. This time it's pushing down. Because the block is stopped, the kinetic energy is 0. And because the spring is compressed as far as it can be in this example, the elastic potential energy is at a maximum. And that pattern is just going to continue to repeat and repeat and repeat over and over and over as long as there's no friction. Now, we know in the real world, friction would stop that pattern from repeating. But typically in this class, when you're dealing with springs or pendulums, we tend to ignore friction unless you're told otherwise in AP Physics 1. All right, remember the other example we're going to talk about for simple harmonic motion is the pendulum. Simple pendulum. So notice here's a picture of a pendulum. We call this the ball part, the bob, the pendulum bob. And notice that the green line represents just a vertical. And angle theta is the angle we move the pendulum away from the vertical. That's our displacement angle. Due to that angle, there's some things we can calculate about our pendulum. Notice that what I did here down at the bottom is I drew in the weight. Remember, weight always acts straight down. So the line that I just drew there in red, that's the weight. We know that's mg. Most of the time, they're going to give you the mass of the pendulum bob in the problem. You're then going to take that weight and resolve it into two components. One component that runs along the string, like this, and another component that's perpendicular to that one, like this. So this component along the string, that represents the tension that's acting in this rope. And then this perpendicular component here is the restoring force. That's the force that's pushing the pendulum bob back toward equilibrium. So we can use some fancy trig to calculate those. Let's assume that we know the mass. So if we wanted to find the size of the restoring force, we could use the sine function. And we could say the sine of theta is equal to the opposite side, which would be our restoring force. I'm just going to call that F, over our hypotenuse in our picture, which would be mg. Well, that means that F equals mg sine theta. So that's how we can calculate the magnitude of our restoring force. We can also calculate the tension in the string much the same way. We can use cosine. Remember, cosine is adjacent over hypotenuse. So here the cosine would be the tension. And I'm going to write that as Ft so we don't confuse that with torque or period. But that's adjacent over hypotenuse, so over mg, which means our tension force is going to be mg cosine theta. And there are going to be problems where we need to calculate both of those. We'll talk about those in a minute. One other formula that I want you to be familiar with while we're here is this one. This is the formula for the period of a pendulum. How long does it take that pendulum to go over and back to where it started? The period of a pendulum is 2 pi times the square root of L. That's the length of the pendulum divided by G. So 2 pi square root of L over G. So really the only things that affect the period of the pendulum, how long is it, and where are you at? What's the force of gravity acting on that pendulum? All right, so let's move on to the next slide. I think we've looked at all this. We can also calculate the displacement of a pendulum, like the linear displacement, by multiplying the length of the cord, how long is the pendulum cord, times the angle theta measured in radians. You're not going to see many problems like that in Physics 1, but if you're asked to determine the displacement of the pendulum, length of the cord, times the angle of displacement measured in radians. Remember that this is an example of simple harmonic motion, so the displacement is proportional to the restoring force and vice versa. All right, so now I want you to go to the Pear Deck screen. And let me get out of this for a second. Get back to Pear Deck. And I want you guys to attempt to answer the first question. So take a minute, see what you can do on problem number 1, and just type in your answer, A, B, C, or D. All right, I'm going to see what you guys are thinking. So it looks like we got an even split almost between A, B, and C. We got another C or C answer or two there. So let's think about it. Let's go back to PowerPoint for a minute. So let's say that here's our spring. And let's say we got a box attached to it. Let's say right in here is equilibrium. But now our spring is stretched out over here to maximum. This is the amplitude, maximum displacement. And that amplitude is 6 centimeters in this case. We want to know what is the total mechanical energy in the system. Well, it's important for you guys to remember that the mechanical energy in a system is equal to what? Anybody remember what the mechanical energy is equal to? Unmute if you do. What two things make up the mechanical energy of a system? Daniel?
Is it GPE and kinetic energy?
Yeah, so it's kinetic. It doesn't necessarily have to be gravitational potential energy. It's any kind of potential energy. So in this case, it's going to be our energy due to our spring, our elastic potential energy. So let's think about this for a minute. When this object is at maximum amplitude, what do we know about the kinetic energy at maximum amplitude? Somebody unmute and tell me what's going on with kinetic energy when this box is at maximum amplitude.
Zero.
It's zero because the box isn't moving at that instant. So that means at that instant, all the system's mechanical energy is elastic potential. So we can use our elastic potential energy equation, 1/2 kx squared, and we can calculate the mechanical energy at maximum amplitude, which turns out to be all of the mechanical energy of the system, because at that point, all of the energy is elastic potential. So 1/2 kx squared, so 1/2. Our spring constant here is 80 newtons per meter. Remember that x needs to be in meters. They give it to us here in centimeters. So 6 centimeters is 0.06 meters. We square that out, do the math, and I've got the math worked on the next slide. So let's get to that next slide. And it turns out it comes out to be about 0.14 joules or 0.14 Newton meters. So B looks good. Remember that answer. I think we're going to need it in the next problem potentially. So that's the amount of elastic potential energy, which turns out to be all of the mechanical energy of the system. All right, now we're at problem 2. So I want you guys to go back to Pear Deck. Let me get back there for a second. And I want you to go ahead and put in an answer for problem 2. Okay, so this one doesn't have to do with 1. We're going to come back to 1 later that has something to do with 1. This is a completely separate problem. So see what you can do with this one. I will tell you, don't overcomplicate this one. It's a lot easier than you might think. I'm going to see what you guys are thinking at this point. So we're kind of all over the place. We got some A's, some B's, some C's, and some D's. All right, so I'm going to go back to Pear Deck or to PowerPoint. So remember, we've got here's our vertical spring. And we've got this weight added onto it. So let's say that this is where the natural length would be. Now we put this weight on, and this thing stretches down an additional 0.15 meters. So that's a displacement. We want to know the value of the spring constant. The way we're going to find that value of the spring constant is we're going to use Hooke's law. F equals negative kx. In this problem, what's the F? What's the force pulling on the spring? Somebody help me out. What's the value of F going to be in this problem?
8.
Yeah, it's going to be the weight of the box. So let's solve this equation. Let's solve Hooke's law for K. So F over X is going to equal K. And remember, the negative sign here just means the direction. So it's not really important for what we're doing as far as the magnitude, the constant. So we really can drop it for now. Or we can think of this displacement being a negative displacement since it's down. That might be the best thing to do. So if we solve this out, so our force is going to be our weight, which would be 0.8 kilograms times G. So that would be 8 newtons. That's our weight. Divided by our displacement, which would be negative 0.150 meters. And that's going to give us our K. If we divide that out, I'm going to go ahead and go to the next screen. Turns out you end up with 53.3 newtons per meter. Again, that's a measure of how strong is the spring. How much force is applied by that spring for every meter that it's compressed or stretched. All right, so here's problem 3. This might be the most tricky one that we have. So I want you guys to take about 2 minutes. Let's go back to Pear Deck. And I want you guys to try out problem 3. And I will take you, this was going to take you 3 good steps really to work it out. So to try to take 2 or 3 minutes, work it. We're going to try to get through problem 5 today. because of our tech issues, we're not going to finish everything I'd hoped to do. So we'll continue this in the next session, but let's try to get through problem 5 today. Take about 1 more minute. All right, I'm gonna look and see what you guys are thinking. So B, C, and D, with C being most popular. So let's go back to PowerPoint. And let's think about what's going on in this problem. So we've got this mass connected to a massless spring. And realize there is no such thing as a massless spring, but they're trying to take out some variables here. So they think about the spring as not having mass. So here's our box on this horizontal surface. So the amplitude, the maximum displacement is 9 centimeters. What is the speed when it's 3 centimeters? So let's say that this is equilibrium right here. We'll call that E. So when we're back here at 9 centimeters, remember back at this point, all of our energy is elastic potential. There's 0 kinetic energy back here. But when this thing starts to head back, because the displacement away from equilibrium gets smaller, potential energy goes down while kinetic energy goes up. And that's as the object is moving back toward equilibrium. So what we need to think about first is that whole idea of mechanical energy. And remember that mechanical energy is the sum of the kinetic plus the potential. At maximum amplitude, kinetic is 0. Elastic potential is at a maximum. So if we use 1/2 kx squared to calculate our maximum elastic potential energy, that'll give us all of the mechanical energy of the system. And we're going to use our maximum displacement. Again, I converted that centimeters to meters. So let's calculate 0.09 squared times 80 times 0.5. And when we do that, we get a maximum elastic potential of 0.324 Newton meters or joules. 0.324 Newton meters or joules. Now, we know that when the box gets back to equilibrium, all of that energy will be kinetic. But in this problem, we're not getting all the way back to equilibrium. We're getting to 3 centimeters away from equilibrium, so somewhere in here. At that point, some of the energy is potential, some of it is kinetic. So since we know that displacement of 3 centimeters, let's calculate how much elastic potential there is at that point. So again, 1/2 kx squared. So it's 1/2 80 times the displacement is 3 centimeters, so 0.03 meters squared. Do the math. So we end up with an elastic potential energy at that point of 0.036 joules or Newton meters. So that's the elastic potential at 3 centimeters. This is the elastic potential at 9 centimeters. This is all of the mechanical energy of the system. Remember that mechanical energy is kinetic plus elastic potential. So if we take this 0.324 and subtract from it 0.036, that should tell us how much kinetic energy there is at this point. So let's do that. Take the total elastic potential energy, the maximum mechanical energy of the system, 0.324, subtract from that 0.036, the elastic potential energy at 3 centimeters. And that gives us 0.288. So at this point, the 3 centimeter mark, we have 0.288 joules of kinetic energy. Now that's not what the question's asking us. The question wants to know what's the speed. So we're going to have to set that equal to the kinetic energy equation, which remember is K equals 1/2 mv squared. So we're going to say 1/2 mass, which is 0.60, times v squared equals 0.288. Solve for v. So I'm just going to go ahead and solve that for v. I'm going to multiply both sides by 2 to get rid of that 1/2. Divide both sides by 0.6 to get rid of the 0.6 kilograms. And then take the square root of both sides. So 0.288 times 2 divided by 60 at 0.60. Try that again. 0.288 times 2 divided by 0.60. Take the square root of both sides. And I end up with about 0.98 meters per second. So that one was pretty involved. The big idea was thinking about this equation, that the mechanical energy of your system is the kinetic energy plus the elastic potential energy. Key to working that problem. All right, so problem 4 should be a lot more simple. And let's go back to the Pear Deck and look at this one. All right, so an object attached to a horizontal spring is set into oscillatory motion, and a position sensor is used to record the displacement of the object from equilibrium as a function of time. The obtained data is graphed below. The total distance traveled by the object between t equals 5 and t equals 9 is. Notice it's asking for distance here, not displacement. So you guys take a minute and try to put in an answer for me. The total distance traveled by that object between 5 and 9 seconds. I'm going to see what you guys are thinking. So lots of C's, a couple B's. Let's go back to the PowerPoint. And before I do that, I see some numbers that I need to change here real quick. And now let's look at the graph. So again, we're looking at the total distance. Remember, distance is a scalar. Direction doesn't matter. So we're starting at 5 seconds, and we're down around -20 is our position. So we're starting at -20. And then we go up to 0, so that would be a distance of 20. and then we go up to positive 20. So that would be 20 more. That would put us at 40. And then we go back down to 0. That's 20 more. That put us at 60. And then we go down 20 more, and that puts us at 80. So our answer on this one is C. Remember, we're asking for distance. Distance is a scalar. The direction does not matter. It's how far you travel. You went 20 up, 20 more up, 20 down, and then 20 more down for 80 total as far as distance goes, 80 total centimeters of distance. All right, let's look at one more problem. Also a graph problem. And let's go back to Pear Deck. And let's let you guys take a minute and try problem 5. All right, I'm gonna see what you guys are thinking. So lots of A's, some B's. So it looks like it's a competition between A and B. And that makes sense. So let's go back to my PowerPoint. Oops. So this question is asking us about frequency. Remember, frequency measures the number of cycles, or in this case, oscillations per second. Well, let's first of all figure out how long it takes for one oscillation, one complete cycle. And you could start it anywhere on the graph. I'm just going to start right here. So our object goes down, and then it comes back up, continues up, and then it gets right here. And at that point, notice that it starts to repeat what happened over to the left. So that red part is one complete cycle. So let's see how long that took. Well, if you count on our axis, it looks like that one cycle took 4 seconds. The time for one cycle is the period. So the period is 4 seconds. So some of you picked A. But remember, this question didn't ask about the period, it asked about the frequency. The period measures the number of seconds for each cycle. The frequency is the inverse of that. The frequency measures the number of cycles per second. So frequency equals 1 over the period, which means in this case, it would be 1 over 4 seconds per cycle, which ends up giving us 1/4 cycles per second, which is 0.250 hertz. All right, questions for me on any of the first 5 problems? All right, I apologize for the tech issues we had today. During the next one of these sessions, we'll finish up these practice problems on simple harmonic motion, and hopefully we'll also have some time to deal with torque and rotation. We'll call it a day there. Thanks again for being here. I appreciate it.